Hey y'all, welcome back to Alakazam Math Made Easy. In this video, we're going to go through a lot of, oops, this is the wrong video. We're going to go through a lot of the beginnings of applying derivatives. So if you've gotten to this point and you're like, Allie, why am I memorizing all these rules, all of these like derivatives? If all we're going to do is calculate them, right? I'm not doing anything with them yet. That's what this video is going to start introducing us to, right? So what do we know so far? We know that the derivative is a function describing the slope of any tangent line at any x value we want of a particular function, right? But what do we know about a tangent line? A tangent line is a line that describes the behavior of the function itself at any particular one x value, right? So looking at this, as usual, all of these dotted lines are tangent lines that I've drawn on the graph at different points, right? So what do I know looking at each of these lines individually? If I'm looking at just the line at this point, what do I know about the function given this tangent line? Well, because the slope of that tangent line is positive, I should know that the function is increasing at x equals a. Same thing, at x equals b, I can deduce something about the actual function given the tangent line based on what the tangent line is doing. And in this video, in this specific drawing, I didn't necessarily do it 100% accurately, but that was supposed to be a horizontal line. And what do we know about horizontal lines is that their slope is 0. So because the slope is 0, I know that the original function is flat at that point, right? So at this exact instance, this function is perfectly horizontal. Same thing, I can deduce something at C, and this line here, this red line, is pointing down, so it's a negative slope, which means that the slope of the actual function is also negative. Moving along to point D here, I can still deduce something. Again, that one is flat, which means our slope is 0, which means at that exact point in time, our function is completely flat, right? And then finally, we can deduce something at E as well, and that is increasing because the slope is positive again. So basically, I don't necessarily want to draw the graph every single time I want to find out where a function is increasing or decreasing, right? But what I can do is I can use the derivative to know that stuff. So if the question is asking you to find a range of values where the function is increasing or the function is decreasing, or sometimes it asks you for both, we'll work through an example on how to do that. But basically what we're going to take advantage of is the principle that we know that when the derivative is 0, the function is flat, which means that sometimes that could indicate that it's transitioning from increasing to decreasing. So that could mean a couple things, right? So let's look at the 3 things it could mean. So first of all, it could mean that the function is increasing and it is now decreasing, and that's why it's flat here. It could also mean that the function was originally decreasing and is now increasing, and that's this flat piece here. But again, that's not necessarily true. It could be increasing or decreasing constantly, something like this. And at this exact instance, this piece right here happens to be totally flat. And actually, this third case is what we're going to look at in this first video, or in this first example. So I was given a function, and that is the function right here. And I want to know where it's increasing or decreasing. So the first step is to find the derivative. So again, working through it really quickly, we'll do that -1, this -1, -1, and x to the 0, -1. So again, 3 times 1/3 is 1, x squared. 2 times 1 is 2, x to the first. 4 times 1 is 4, x to the 0, and 0 times 2, x to the 0, or to the -1 is 0. So that's where we get that. And what I'm going to do now is I'm going to solve this equation for 0, because remember, we're just what we know that all of these situations have in common is that there's some point where it flattens out. And if I look at either side of these points, I can tell whether it went from increasing to decreasing at that point, or whether it went from decreasing to increasing, or if it didn't change, if it went from increasing to increasing. So that is the goal. So we're going to find the x value that corresponds to that transition, right? And it's not always going to be 0. That's just how I drew these graphs. So here in this case, we find out that by setting the derivative equal to 0, we get x equals -2. So the easiest way to define or to write out your logic is to then draw a number line with x equals 2 in the middle, right? And we're going to evaluate, like I said, we're going to look at either side of that point and determine whether the function's increasing or decreasing. So remember up at the top, we said that because the slope of this tangent line is positive, that must mean that the function is increasing. And if we're looking for the slope of the tangent line being positive or negative, we're actually looking for the derivative being positive or negative. So we're going to do the same exact thing down here. I'm going to go to my next step and I'm going to test a point on either side of that critical value that I found here, right? So the first one I'm going to test is x equals -1. And that's going to tell me if the function is increasing or decreasing to the right of x equals -2. So what I'm going to do is I'm going to plug in x equals -1 into the derivative and see if the derivative ends up being positive or negative. So by plugging it into the derivative, I get 1, which is very clearly positive. So that value is increasing. I'm going to do the same thing for the value to the left of -2, and that's going to tell me what the function is doing left of that critical point, right? And in this case, plugging that value in also gets us 1, which means it's also increasing. So how do I write that? So I write that by saying the function given, right, this was given, is increasing, which is what it was asking, over this range of x values. And you could also write that by saying, usually what they like to do is they like you to break it out into sections based on what your critical value was, right? So you could say that that means that this is -infinity to -2 union, which means we're combining these two things to infinity, which is essentially what it means. The same thing as this one up here, but it's written in the way that a lot of math teachers like to receive it, right? Couple notes. Any parenthesis that's next to an infinity or -infinity should not be a bracket, it should be infinity. And any bracket that's up to a critical point should not be a bracket either, because those are, it's not increasing at that value, it's actually transitioning at that value. So you can't include that in the range that it's increasing because it's by definition not increasing at that value. So remember a couple videos ago in the higher derivatives video, higher order derivatives, I'm sorry, I went into the concept of a second derivative and I promised that we would bring it up again in the future. We can do the same thing, same exact process with the second derivative to find out where the function is concave up and where it's concave down. So instead of being increasing or decreasing, we're now looking at the concavity. And the way to remember which is which, concave up, what shape that describes, and concave down, what shape that describes, is to remember cup and frown, right? Concave up looks like a cup, right? I could draw a little cup here. And concave down looks like a frown, like I could draw a frowny face here. So those are the ways that I remember it even to this day, right? So the second derivative, following the exact same process, but with the second derivative instead of the first derivative, shows us where the function is concave up or concave down, right? So let's work through the same exact problem that we had before, this time looking at concavity instead of increasing, decreasing, right? So this is our first derivative, but we want our second derivative. So we're actually going to take the derivative of that. So remember 2 multiplied to the front minus 1, 1, 2 minus 1, and then a constant goes away. So that's where we get the 2x to the 1 times 2x to the 0. So that's our second derivative. And we're going to set that equal to 0. And we're going to solve for that x value. And then we're going to build our same number line just like we did before and test numbers on either side of the x value we found. And we're going to find whether it's positive or negative, right? So if I plug in 0 into the second derivative, right, because we're testing concavity, we look for the second derivative. Just like when we tested slope, we looked into the first derivative. So here we're looking for concavity, so we're going to plug in our values into the second derivative. So I plug in 0 into 2x plus 2, and I get 2, which is positive, so that means it's concave up, which means at this point, so generally if I was to graph this function, at x equals -1, this function starts doing something like this, right? It starts switching to concave up. And now I'm going to plug in x equals -2. I get 2x times -2 plus 2, I get -2, which means it's concave down, which means at -1 to the left of that, it starts going concave down. And if you compare these, so this is the -1 that we've been using. If you compare these, you can tell that that does mirror the fact that it was increasing and remains increasing, right? So these are actually two concepts that work together a lot of the time, right? And that's what we're going to do in this question here. We're going to combine them and we'll work through it together. So this question is actually asking us to draw the graphs, right? So a couple things we need to know: where is it increasing and decreasing, and where is it concave up and concave down? So we're going to look at the general slope changes, and that's going to be our increasing, decreasing. And then next we're going to look at concavity. But let's look at y prime. We know that that's going to be x squared plus x minus 6, right? Because that's just taking the derivative of this piece here. I'm going to set that equal to 0. What's nice is that that factors pretty well. So we're going to get x plus 3, x minus 2. So what did I just do? X plus 3. So we're going to get x equals -3 and +2. So now what I'm going to do is I'm going to plug that into a number line, right? But because I have two values, I'm going to put both of them on there. And I actually have to test all three of these ranges. So I'm going to test -4, I'm going to test 0, and I'm going to test 3. So if I'm testing -4, I plug in -4 plus 3 and -4 minus 2. And that gives me -1 times -6, which is +6. So that is going to be positive here, which indicates that it's increasing to the left of -3, right? And then 0, I'm going to plug in 0. I'll get 0 plus 3 times 0 minus 2. And that gives me 3 times -2, which is -6. And that's negative, so that shows me that between these two values, the function is decreasing. And then lastly, I'm going to plug in +3, so I'll have 3 plus 3 times 3 minus 2. That gives me, that gives me 6 times 1, which is +6. And that shows me that, again, it turns into increasing, right? So basically what this does is it shows us that the function is increasing from x equals -∞, comma -3, and then it stops increasing, and then it goes to increasing again at 2, infinity, because it increases everywhere after that. But that also means that it's decreasing for everywhere that x equals -3 to +2. Sorry, not negative. But what's interesting is that you can almost check your ranges and that you have everything because it should piece back together to cover any possible number, right? So here we go from negative infinity, so that covers all the numbers up to -3. And then we pick up again at -3 and go to -2. And then we pick up at -2 and go to infinity. So we actually do have all of our numbers covered that we could possibly want to plug in. So that's that. But that's not enough to draw the graph because I don't know anything about the actual shape aside from the fact that it's increasing or decreasing. So what I'm going to do now is look at concavity. And I know that my f prime of x equals x squared plus x minus 6. So I'm going to take the derivative of that again to get my f double prime. That gives me 2x plus 1. I'm going to set that equal to 0. And when I solve, I get x equals -1/2. And again, I'm going to build a number line. This time I only have the -1/2. So what I'm going to do is I'm going to test 0 on this side and -1 on this side. So I'm going to plug that into my second derivative, remember. So if I plug in 0, I get 2 times 0 plus 1, and that gives me 1, which is positive. So this is going to be concave up on this side. And then I'm going to plug in -1. So I have -2 plus 1 is -1, and that means it's going to be concave down on this side. So here's what I know so far. Here's what I know. I know that I have this function, right? And I'm going to do -1, -2, -3, 1, 2, and we'll do 3 just for good measure. I know that it changes concavity here, and I know that it changes slope at these points. What I don't know is any of the x values where this stuff happens, right? So what I'm going to do now, I'm sorry, any of the y values. I know the x values, but how can I graph a function if I don't know where the function is? So there's a couple ways to do this. And depending on the way that the question is worded, it'll lean towards one or the other. I'm going to do it the way that I think is easiest, right? So what I'm going to do is I want to find the y values where all of these three things happen, right? Sometimes the professors will ask you to find the zeros of the function, in which case you set the original function equal to 0. I'm going to solve for the values of the original function at each of these 3 points. So f of -3 will tell me where that function originally stops increasing. And remember, the original function is, maybe I should write that down first. F of x equals 1/3 x cubed plus 1/2 x squared minus 6x plus 17.2. Wow, I could have made that a little bit cleaner, huh? So if I plug in f of -3, I'm going to get 1/3 times -3 cubed plus 1/2 times -3 squared minus 6 times -3 plus 17.2. And that's going to give me -9 plus 4.5 plus 18 plus 17.2. That'll work out to, let's see, 18, that'll be 25.2 minus 4.5. That'll work out to 20.7. So I know that at x equals -3, I have a y of 20.7, so a little bit higher than that 20. So that's a true point that I have right there. So now let's try f of -0.5. That's going to be 1/3 times 0.5 cubed plus 1/2 times 0.5 squared minus 6 times -0.5 plus 17.2. And for the sake of saving you guys time, let's call that 1.5, right? So at 0.5, we'll call it 10.5 or 11.5. So it's easier on the graph. So here's 10. We'll call it a little higher than 10. We'll call it here. And then if we plug in 2, this is not the actual number that it comes out to. Let's call it 15, right? So we'll call that halfway point between here. So let's piece together the information that I know. I know that from -3 to the left, it has to be increasing. So essentially it has to be doing this. But I also know that from these other places, from -3 to -2, it has to be what's it called? It has to be decreasing. So generally from here all the way to here, it has to be in decreasing. But I know that for everything left of this 0.5, it has to be concave down, right? So that this means even though this is increasing, this still has to be concave down to that point there. So let me draw this a little bit easier, right? So it has to be concave down. And at that exact point, it starts to smooth out a little bit, right? So here it's going to turn back up, start still decreasing. Actually, what I'm going to do is I'm going to decrease this point a little bit. So it's going to still be decreasing, but it's going to be concave up. So see how that function is still decreasing, but it's cupped upward, and then it starts increasing again here. So obviously that's not what the actual functions look like. I'll call this 8 instead of 15 to adjust for that change I made. This is not the actual function. On an exam, you would find what these actual numbers are. But for the sake of the video, I figured I'd cut it short. But yeah, so you need 3 things when you're actually building the graph. You need the range that it's increasing and decreasing. You need the range that it's concave up or down, but you also need the actual function values, either at the zeros, if the question asks for that, or if it doesn't, if it lets you choose your own way. I personally find it easier to just find the y values where this stuff happens. So if you learned something from this video, give it a like. If you want to keep up to date with the content that I post on this channel, subscribe and press the notifications button. And as always, if you have questions, leave them in the comments. Otherwise, best of luck.